Hello everyone, thank you so much for being with us today. I'm Wayne McCullough. With me is one of our distinguished alumni of Susquehannock High School, Dr. John Berthold from the class of 1963. Today at commencement, John will be honored and have the opportunity to speak to our graduating seniors as well as to their parents and class members and community members. So, Dr. Berthold, it's so nice to have you here. Thank you so much for joining us today all the way from Ohio.
Well, thank you for the invitation. I'm happy to be here.
Good. Let's start. Tell us about some of the activities that you participated in while at Susquehannock High School, and then we'll chat a little bit about just growing up in southern York County.
Okay. Well, I tell you, I was actively involved in the musical programs when I went to Susquehannock, and if you had to ask me to pick out one thing that I remember, I had the most fun when we would be on the bus and go to the away football games, and we would do it, on a regular basis every fall. We would have conversations, we would laugh, and then coming home we would sing. It was just a great time. And all the band and the majorettes and the color guard were all on the same bus. It was fun.
Yeah, now John and I have already had the chance to chat for a little bit, so I'm warning you right now. I'm a storyteller and John is too, so you're in for your hands full. But I coached basketball here for many years. Here's my story about that. We were at Littlestown, we played a game, our kids just won, and we're coming back on the bus. And I'm sitting there with our assistant coach and there was no talk going on the bus. And I look back, kids have their headphones on, they're on their cell phones, and I said the same thing. I said, our favorite time while we were playing was the talking and the interaction.
Yeah.
And my son played on that team, and here's the end of that story.
Mm-hmm.
First of all, he didn't communicate all the way home on the bus. I came home, he went home, and I came after all the children were picked up. Mm-hmm. And in our living room, in our computer, I got home and he was having fast chats or instant chats on the computer with 5 or 6 people he just sat on the bus to and didn't talk with. So I'm thinking the world has changed, but no, you're right. The memory of those interactions with our classmates,
those interpersonal things, and that's why I remember my friends so well growing up.
Yeah.
And if I had just corresponded with them by email or Instagram or something like that, I would not know them like I know them now, and remember them like the way I remember them now.
Yeah, now you grew up in New Freedom.
Right.
Tell us a little bit about life in New Freedom as a child and what that meant to you.
I think life in New Freedom when I was a child was the same as it was when my mother grew up in New Freedom in the early 1900s.
Okay.
We walked everywhere. I walked to school. I would come home for lunch. My mother would ask me in the morning what I would like for lunch, so I knew what to expect when I got home, and it was wonderful. And I had other friends, of course, who lived all over New Freedom, and so we would go and visit each other after school, or we would take hikes after school, and sometimes our mothers didn't know where we were, but we were always home by dinner.
Right. When you went to Susquehannock High School, was it grades 7 through 12?
Grades 7 to 12, right.
So you went right from New Freedom Elementary School to Susquehannock High School.
Yeah, when I was in the first grade, that was the first year of the consolidation.
Okay.
Yeah. So I started in first grade in 1951. And then my sister, who's 10 years older, was in Glen Rock for the first half of that year in 1951. And then they moved to Susquehannock here in the beginning of 1952, I think, for that second two grading periods, I believe is right, isn't it? The second two grading periods?
Yes, that's correct. The second half of the year,
right?
Mm-hmm. Yeah. So you were involved in the music department. I know you were also the valedictorian of the class.
Right.
Tell us about some of the other things you participated in, please.
Well, one thing I mentioned in my bio that Mark picked up on was setting up an emergency communication system. Is that what you want me to talk about?
Please, yeah, thank you.
Yeah. Well, that came about, and let me tell you how that came about. Calvin Stott, Mr. Stott, was the vice principal, or assistant principal, and he later became the principal at Gettysburg High School. But in that time, when I was a junior, he would always advocated the trades and the industrial arts, and he thought that was important in high schools to teach that. And I certainly got a lot out of it too. We had a great agriculture program, and Russell Hare was the teacher of the ag group. And then we had Paul Huddle, who was the teacher of industrial arts, we called it, and he taught mechanical drawing, woodworking, and machine shop methods. And so we learned how to cut metal, we learned how to drill metal, and if you were in the woodworking, you learned how to do the same thing with wood. So, I specialized in the metal, and I enjoyed that. So anyway, Mr. Stott, the assistant principal, was always interested in what Mr. Huddle was doing, and somewhere along the way, Mr. Stott learned that I had an amateur radio license, and I had gotten my license when I was 13. So my junior year, he learned about this, and he said, you know, we really need an emergency communication system, and maybe you can help me with this. In the event of a loss of telephone service or electricity, of course I couldn't do much about the electricity then, but that was his goal. We would need to communicate with Friendship Elementary, and those were the two schools in the school system, not counting all the elementary schools, but Friendship was the new one, and that was line of sight. And I said, well, that's line of sight, I should be able to do that. But in order to do it, I had to get permission from the Federal Communications System, the FCC, Federal Communications Commission, to have Susquehannock be a base station.
Wow.
And it had to be supervised by a radio amateur, and I would have been that person. But this program was called RACES, Radio Amateur Civil Emergency Service. So we were certified to do that.
Wow.
And now I spent my senior year then working to get this thing up and running, and I had friends that helped me, and we put an antenna up on the roof near where the old band room, the curved band room, meets the main building. You may even remember that antenna was up there for many years.
I do remember.
And there's another antenna there now, but it's a much shorter wavelength. It's a microwave antenna. Is that right, Mark? Yeah. Now, so that's about 6 times higher in frequency than what I installed. But what I installed worked, and when I graduated, I was hoping that someone could take my place as being the one in charge of the base station. So I don't know whatever happened to it, but that's that story.
What started your love for science? Is there one thing, a couple of things?
Yeah. Back in the beginning, when I was little, I developed a way of thinking about things, and so now I got to go back that far. I learned how to think in 3 dimensions. So when it came to puzzles, I didn't care about jigsaw puzzles. I cared about solid puzzles that needed to be put together from pieces. And I was fascinated with that from the time I was little. So from that, I went to, rector sets and making things with the rector sets. And then I got a chemistry set and a microscope. And the optics part of it fascinated me. So that's how I really got started. But then the radio part of it came along when I was 11. And my father gave me one of his books from when he was a boy. It was called The Boy Electrician. And it was written in 1912, and it described in there how to make crystal radios. So I built crystal radios from the instructions in that book, and just was amazed that I could do that.
Yeah.
So that's what got me started. But now making things and having them work is one thing, but understanding how they work is something else. And that's really what I wanted to do, is not just, why is this and what is it? And you can make one, but how does it actually work? And that is a long journey.
Again, we're speaking with John Berthold from the class in 1963. John was class valedictorian, member of the National Honor Society, a class officer, a member of the Calumet staff, which is our yearbook. You already mentioned the concert band, the marching band, the dance band. One of the things I thought was very interesting is you were a member of the district band, but also the district orchestra.
Right.
Because I know you played the string bass as well.
Right.
And my son, we played the trumpet in the string bass, so I saw
Oh,
that connection
yeah.
there too.
Yeah.
Which was interesting. So, you were very active in high school.
Mhm.
Obviously, sounds like a very good experience. Is there
Oh.
anything else you want to mention about your high school experience?
Well, off the top of my head, no, but I'm sure there are things.
Okay, we'll probably interweave them as we move throughout. From here, John left Susquehannock High School, went to Gettysburg College.
Right.
Tell us a little bit, reflect on your years while at Gettysburg.
Let me go back to answer your question about my time here. For the last 20 years, I've been in charge with a lot of help from my classmates, in charge of the reunions. And we have a lot of people that come to our reunions, and we have had a great time. And that just reinforces, my love for this area.
Yeah,
I'm a York County guy.
you are. Yep, absolutely. Now, hold on, I gotta grab something here out of my closet that I've been saving for this moment. Because John, you gotta explain this. Here is John's class jacket, which is a green Susquehannock. I'm knocking over our things.
Oh, no, there's
A
nothing
green-
in there.
This is green Susquehannock jacket.
Yeah.
And every time I show that to our alumni groups, in fact, when I give tours to our alumni, I bring that along and I
Yeah.
share it with them.
Yeah.
And they're all saying, how did they have a green jacket? So explain that.
Well, in my day, we had the school colors. Now, back then they were maroon and gray, and even our band uniforms were maroon and gray. And I'm sure as time went on, you learned that maroon and gray were not at the top of the list of school colors, and maybe it cost a little more for maroon and gray, so you changed them to red and white. But back in our time, we could have class colors. So every class had their own colors, and our class colors were green and white, and we could get our Susquehannock jackets made from those colors. So I got my name engraved on this side, or embroidered, and then on this side, Susquehannock class of '63. And when we had our 50th reunion here,
Okay, thank you.
yeah, when we had our 50th reunion here in 2013, we had an event on the football field at the home game. It was homecoming, and that's why we scheduled the reunion for homecoming. And we invited football players from my class to come back, and they were recognized at halftime. They all went out onto the field, and that almost didn't happen because of the flooding the day before.
Sure.
So and it all worked out. So anyway, we had a game, we had the recognition, and I was wearing that jacket. And I had students come up to me, and they couldn't believe their eyes, and they wondered, were the school colors green and white in your day? And I said no. Our class had green and white, and we could have jackets made with our class colors.
Yeah, that's
So, and
great.
one student said, well, how much do you want for that? I said, well, no, it's not for sale. But then I got to thinking later, maybe I should donate it to the high school, so I did.
Thank you, that's very nice. No, and it's amazing the conversations that's generated, which is wonderful.
Good.
All right, now we'll get to Gettysburg College and reflect on those years, please.
All right. Well, I was fortunate to get accepted at Gettysburg my junior year. And my sister went there, and so maybe I had a little bit of a legacy, but they had an option to apply your junior year, and if you accepted, you were committed to go, and you had to make a deposit. So I did that. And I originally had the intent to go for the 3-year program, which in those days I could go 3 years to Gettysburg and 2 years to Johns Hopkins or Penn State. I would have gone to Johns Hopkins. And at the end of 5 years, then I would have had a bachelor's degree from Gettysburg and a master's in engineering from Hopkins. But I got to Gettysburg, and I really enjoyed the physics department, and my professors were wonderful. I knew a little bit about the physics department ahead of time, and I knew that's what I was going to major in. But once I got there, there was no question I was going to finish at Gettysburg, so I did.
Okay. And while at Gettysburg, really became the initiative of your career.
Yeah, once I got there,
elsewhere.
and I realized, yeah, you can really do physics. You can figure things out. You're good in math, but you have to be able to apply the math to the real world, and I could do that. And that's the important link here. Not just the math, but to use the math to relate it to the real world, and then to be able to model things and predict performance. And that's what engineering and science is all about in the working world.
Okay.
I learned that at Gettysburg.
Yeah.
But I got the fundamentals here. I could not have gone to Gettysburg and majored in physics without what I learned here.
Okay. And the story is that while at Gettysburg, you somehow saw or were part of an experiment with a laser, and that interests you. Do I have that right?
Yeah. The laser was invented in 1960. In fact, the whole optical technology had breakthrough after breakthrough in the magical decade beginning about 1958 and ending in 1970. That so much happened then. The laser was invented.
Okay.
Optical fibers were invented, and then they were perfected by Corning in 1970. And there were other things to go along with all of that, but it was an exciting field to be in. So when I got to Gettysburg in 1964, the laser was only 4 years old, and most colleges were just learning about it, and they had one there at Gettysburg, and it just fascinated me. So that's what got me going in optics and optic technology. It wasn't about lens design or any of that, although I know how to do this, but that's what got me started, was that laser and trying to understand how it works. And it's a fascinating device. It's coherent, and radio waves are coherent. But what does that mean, coherent? It means getting all the atoms to emit their light in phase.
Okay.
Just like, waves of soldiers marching in a parade, they're all in step, and you hear the sounds as they take their steps. They're marching coherently. They're not just running around randomly.
Right.
And if you have atoms that do that, you get white light. When you do coherence, you get a single color with feedback from the mirrors on either end of this laser. So a laser has two mirrors, and it's got atoms in between that are excited, and they're caused to emit together in phase.
Wow.
When you learn that, you begin to appreciate, this is state-of-the-art technology.
Yeah.
Yeah.
And we're hearing it from one of the true experts, Dr. Berthold, recognized worldwide for research in lasers, optical use of lasers, but also films.
Fiber optics and fiber optic sensors.
Yeah.
Using glass instead of wires to do sensing. And that has a lot of advantages in industry, especially if you have a lot of, say in a power generation plant, you've got a lot of noise there because you've got generators running, and you have lots of potential for interference. You have problems with what are called ground loops. Just having a wire, the wire will pick up the AC signal.
Right.
It's so intense and provide interference to your computers and everything else. If you have optical sensors, you have none of that because glass is not a conductor, and optical fibers are made from glass. And I was at the forefront of that technology, fortunate to be at the forefront. And so I've done a lot in adapting traditional measurement techniques like pressure transducers and accelerometers and things like that to work with optical fibers rather than electronic wires.
Let me just give our folks just a little bit of a background here. John has either authored or co-authored 75 journal or conference publications on the topic of optics research, holds 51 United States patents as the inventor or co-inventor as well. Just incredible. Let's try to talk about where you left from Gettysburg, what happened, and then I want to spend a lot of time here you just showing some of the things you have, because it's amazing, and it almost is like a science, a show on science for our students to watch, and I think all of our folks in the community will enjoy it.
Mr. Wizard, do you remember him?
I do remember
Yeah.
Mr. Wizard.
Yeah,
right.
this is sort of the kind of thing he would do. Yeah.
Right, so wonderful. So maybe move us from Gettysburg to...
And from Gettysburg, I went to work, and I knew I would probably need more education, but I wanted to get into the working world. and get exposed to the advanced technology. And I was fortunate to get a job at Bell Telephone Laboratories, which is an industrial research and development lab. I was right out of college. I went there for an interview. I got 2 job offers from 2 different departments. And so I decided that I wanted to work in the optical communications part of it. And they were developing tunable lasers. Now, when lasers were invented, they were a single color. Well, if you want to make them practical, you have to be able to tune them. So I helped in experiments to determine how to make a laser tunable. And part of it involved making mirrors to provide some way to cause a feedback from the laser over a wavelength range. And I did programming of the equations to make that happen so that I could predict the performance of this mirror and then use the information to actually design and build one. And that was my first patent.
Wow.
And it was used in the tunable laser research at Bell Labs in those days.
Now, did you have, what I find fascinating, because of your work with lasers, do you kind of fall into the application once you're doing it, or do you have a vision of how that applies before the work begins?
Well, no, that's a good question. And when the laser was invented, it was termed the invention without an application. And that's because, gee, this is a neat thing, but what are we going to use it for? And if you think now about everything it's used for, you wonder why people didn't realize what it could be used for.
Yeah.
But the Bell system knew that it would be a way of communicating that would have tremendous bandwidth, because the frequency of light is so much faster than radio waves. So you can pack so much more information into one light beam than you could for the whole communications in the United States could all be fit onto one light beam. Just imagine that. So that was, that was a vision. But to get there, between 1964 and 1990 was a lot of technology development.
Yeah. Tell us a little bit more about your first patent and what that was used for.
Yeah, the first patent involved depositing thin layers of dielectric material, transparent material. Magnesium fluoride is one of the materials, and that's used on a camera lens to reduce the reflectance of the lens. But the other material was zinc sulfide, and that has a higher index, higher than glass. So by alternating these layers, one versus the other, and doing it in pairs, you can make a very wideband mirror that covers the entire visible spectrum. And that was the goal of the tunable laser, was to be able to tune it over a very wide spectrum.
Okay.
Now, you also needed to introduce a pump signal to excite the atoms in the laser. So you had to have a transparent region with no reflectance. And so I designed this mirror to have approximately 90% reflectance on either side of this region of almost zero reflectance.
Okay.
So that the laser could be pumped, and then the output could be tuned on the wings on either side.
Amazing.
Understand it? Yeah.
No. I'm going to take your word for it.
Yeah.
But what
So-
since
so-
then has that been used for?
Well, it was used at that time for tunable laser research. Today, my design has been refined, and it's the techniques really that enabled wavelength division multiplexing of optical signals.
Okay.
And those filters have a really sharp rise, and their transmission is phenomenal. It's almost 100% transmission. But then up here, there's no transmission. And these steps, if you want to think of them like that,
Okay.
they're called sharp cut filters. So everything here gets transmitted, everything up here gets reflected, but that rise can be just a few nanometers, and a nanometer is a 10 to the minus 9 meters. The wavelength of green light is 550 nanometers.
Okay.
But these can be closely spaced, so now you can separate individual signals at different light wavelengths.
Wow.
And if you have all the spectrum coming in, and you have in your FiOS box, so if you have a fiber optic cable coming into your house,
Yeah.
you'll have one of these filters in there, and it will pick out your wavelength. And that will feed you, and all the others will just go through to the next house, and they'll have their wavelength, and theirs will be separated out.
Amazing.
So the kind of thing I did, even though it was for a tunable laser, has been refined for this wavelength division multiplexing. But there are a lot better engineers and thin film designers that came along after me that did something I could not have done in 1968.
Right.
So
Right. Different equipment.
I made a
You were
first
the ground
step.
of it. Right.
Yeah.
Right. After Bell, tell us a little bit of what you did after Bell.
Well, I knew when I was there that I wanted to be a leader in the technology, and I knew I could do it. I didn't want to be a follower, and so that's why I left. But I accomplished so much in 2 years and 4 months. I was energized and motivated. So I had to make a choice. Where am I going to go to study optics technology? And there were 2 schools in the country back then: University of Rochester in Rochester,
Makes
and
sense.
University of Arizona.
You're Corning, obviously, with Rochester.
Yeah, it's
Right.
close. Yeah, Corning and Rochester are close. And Bosch and Lomb was in Rochester, and they made cameras and lenses and things like that. And of course Kodak.
Right.
But I decided to go to Arizona because they were starting a new program. A lot of the professors there were young. Some were only 10 years older than I was. And so that's where I went.
Okay.
And their program now is world renowned. And there are lots of other schools now that have programs in optics.
Okay.
And for my dissertation research, I measured changes in length using a laser interferometer to measure small changes in length. And I measured the thermal expansion of many materials to 1 part per billion. And you know, a material expands when it's heated up and it contracts when it's cooled down. But the actual amount of that is important in many applications. So to measure it precisely was important. One of the things we measured was silicon. Silicon, you know, is used in all integrated circuits now. We made precise measurements of silicon. Nobody else had them until we measured them. And so that information was used in design of integrated circuits and temperature control and things like that. But the other thing that happened is we got a contract from NASA, the National Aeronautics and Space Administration, and they asked us to measure seven different types of materials. 2 were metal, and 5 were glassy materials.
Okay.
One of them was Corning ultra-low expansion glass, and we knew what they all were. We made precise thermal expansion measurements, and then we also measured the dimensional stability. So we built temperature-controlled chambers and put these materials in there, held the temperature constant, and looked for changes with time.
Wow.
So we had all that data for NASA, and that project was completed in '76 when I left
Okay.
with my PhD. And then in '77 I got an award from NASA too, because of that work. And I didn't know what it was used for until 1990 when I learned that the Hubble telescope, which had just been launched, well, first of all, we heard that it was nearsighted because of a configuration problem in the
Okay.
grinding of the mirror. But when I learned that it was Corning ULE, then I knew why I did all those measurements, because Corning ULE, ultra-low expansion is what it stands for, was the material that had the best performance in all of my testing.
Wow. Unbelievable.
And the thermal expansion is so small, it actually has a crossing at 0, which means if you depart a few degrees on either side of the thermal expansion, if it's 0, it's not changing at all.
Okay.
So that was ideal for something in space where half the time it's facing the sun, the other half the time it's not facing the sun. Otherwise, the heating and cooling of the primary mirror, which is what this material is used for, that primary mirror, the heating and cooling would cause a deformation and an out of focus condition just because it was being heated by the sun or not heated. Well, this stuff was so good that was never a problem.
Wow, unbelievable.
Yeah.
That's
Corning
great.
ULE, and they still make it, yeah.
Unbelievable.
It's a titanium silicate, silicon dioxide with titanium metal in it.
Okay. Now, you actually came back then east after Arizona and worked for NASA as well.
No, the National Security
Oh,
Agency.
National Security, gotcha.
NSA.
Right.
Yeah, you got there's an extra letter in there.
Yeah, and I actually asked Mr. Real about that earlier, so I had that, but right. Tell us about that work.
Well, at NSA, of course it was all classified, but they were interested in optical communications. Their mission is cryptography and coding and decoding messages, and they realized the potential of optics for doing that. And so those are the kinds of projects that I worked on. But the other thing they do in order to code messages is they have to develop what's called a pseudo-random sequence, and then you mix that with your signal, and you have to have a key to get the signal out.
Okay.
So, but I worked on ways to generate a pseudo-random sequence of optical pulses that was random.
Wow.
Yeah.
Unbelievable.
And it required developing optical logic gates. And optical logic gates are like electronic logic gates. You use pulses to do Boolean operations in the binary system. You know, you're dealing with ones and zeros, pulse or no pulse. And I did that with optical signals rather than electronic.
Okay, we're going to have Dr. Berthold show some of those things in just a little bit, but I also want to talk about your family. You have a wonderful wife, Jackie, who's actually with us here today. Tell us a little bit about your family, please.
Well, I'm going to talk a lot about, not a lot tonight, but I'm going to mention them all tonight.
Good.
So let me just talk about my son and my daughter, because I'm not going to talk about them tonight.
Okay.
I'm going to talk about my ancestors, the ones that came before. Jackie and I have a son, John, was born in 1978, and he went to the General Motors Institute in Flint, Michigan. He's an Eagle Scout, and he had a lot of different job experiences. Now he works in Owings Mills for a company called EMG, and they inspect large structures, factories, commercial buildings, apartment buildings, and their primary customers are financing companies like banks. And if somebody wants to buy a building or sell a building, the bank has to do the loan, and they want to make sure that this building is safe and that it meets all building codes. Now, he's not the engineer that does that, but he's the one who collects all the data from the engineers who are out doing the inspections and tells them what they need to look out for, especially in terms of local building codes.
Okay.
This is a nationwide company, and they have offices in every state.
Good.
And he's single, and he lives in Hampstead. Yeah.
Good.
Our daughter is about to have our first grandchild, and she's in Brussels, Belgium. And she went to Cornell University, and she had married a Frenchman. And she took her junior year abroad. She didn't meet him then, but she fell in love with Europe.
Okay.
And she had an opportunity after she graduated to go back and work for 2 years in Europe. And when she did that, that's when she met him. And they've been married since 2008.
Very nice. I can only imagine, and I say this in all respect, I hope it doesn't come across a little silly. When I go home, at the end of the day, I'm sitting with my family around the dinner table, I may say, we had a pretty good day at school. Did anybody around the dinner table understand anything you would talk about what you were doing?
Yeah, my son could understand.
He got it, okay.
Yeah, he got
Interesting.
it. And he would always ask good questions, and I would have to talk to him and explain it so that he understood it.
Yeah.
Yeah. I'm sorry that you didn't understand everything I was saying.
No.
I hope that Mark understood 90% of it. No? Yeah.
Well, no, it's fascinating.
Yeah.
I understand enough
Yeah.
to say, my goodness. In my mind, even though I can't put together and actually maybe relate to exactly the technology involved,
Yeah.
my mind is always, I guess the one similarity we have is how is it used? What can it be?
Exactly, yeah.
You know,
Let me give you my perspective on this.
Yeah.
You know, for hundreds of years we had horses and wagons. We didn't have automobiles. Why not? We know how to build a wagon,
yeah.
but we didn't have an engine. We didn't have an internal combustion engine. So automobiles just didn't all of a sudden appear. They evolved from what we knew how to do. We knew how to make a wagon. So when we had to make a vehicle that wasn't a wagon, we started with a wagon. When we had an engine, we put the engine in the wagon, and it worked. So
Right.
now it's evolved into something. It's a compartment, and it's surrounded by safety features. So if we have an accident, we hopefully won't die. This engine has been developed so that it's very fuel efficient. All this evolution took place after we had an engine, and the optics is like that. When we didn't have lasers, we didn't have communication systems. When we didn't have optical fibers, we didn't have optical communication systems.
Yeah,
So
that's good, that's wonderful.
that's how it happens.
Okay.
Yeah.
And you were there, I mean.
I was there
you
at the
were there.
beginning. Yeah, like being at the beginning with Henry Ford and doing engineering for him. I was at the beginning of the optics technology explosion.
And you're still involved today.
I'm still involved with a small company that builds sensors and instrumentation in this industrial applications area
Now,
to
do they come to
replace
you with-
electronic sensors.
Do they come to you with a problem, saying we're having trouble? with-
No, we make what we can make, and we try to adapt it to commercial products
Okay,
that are a form, fit, function replacement for what's in there.
gotcha.
But instead of wires coming out, we have fibers coming out. And of course, then the demodulators and modulators are part of this system too, so we get to sell those.
Amazing. Let's show us some of the examples of the technology you brought with us, and this may now come across as a little bit of a science experiment. That's good. I think that's what makes it really interesting.
Yeah.
So share some of the things you brought, John.
Well, these are simple things. This is a color absorption filter, and this starts out as pure glass, but then cobalt is added, and cobalt absorbs all the light except the blue. So this is a cobalt blue filter.
And it's used again for
Various photographic applications and for spectroscopy. You know, if you're looking at light emissions from excited atoms and you don't have a spectrograph, which is an instrument that makes precise measurements of optical wavelength, before you put it into a spectrograph, you can put it into something like this just to get a general idea of what the emission spectrum is.
okay.
So if you shine red light through that, you don't get anything out. Oh, this is a silicon crystal, and that's from the 1960s. Now, silicon wafers, this is a solid single crystal, and it's about 1 inch diameter. Now, you can buy these up to 12 inches in diameter that have integrated circuits on them, if you can believe that.
No, I can't. Wow.
Yeah. Well, this is red. So like the blue filter, which only passes blue light, this one only passes red light. Yeah, then related to what we do now, and I don't know if you can focus in on these, this is a piece of glass, and it has a thin film coating on it. It's 5 layers, and one of those layers continuously varies in thickness from one end to the other. So it's like an oil film floating on water. You've seen colors from oil films. Yeah, that's similar to what this is. The thickness varies, which is why there's a coloration. If the thickness was uniform, this would have a uniform color. Right behind it, there's another piece of glass, and if Mark can focus in on that, you see a series of parallel lines on this one. Can you see that, Mark? And those parallel lines are equivalent to what's here, only compressed. So each of those lines has the same spectrum you see here, but only compressed into one line.
Do you ever get involved in, you talk about the manufacturing operation, I'm sure you have to have input there somehow.
Oh yeah. I designed this, and I have a recipe for how it's to be manufactured, and we have suppliers that can make those.
Okay,
Yeah.
wow.
But they don't need me anymore for the day-to-day operations. They just
Right.
make sure that it passes our quality control tests after they are
Okay.
done and we receive them. Now this is a camera lens, and this is a multi-element lens, but it's got, I say multi-element, there's more than one lens in here. Now here's a single lens, it's biconvex, and there's a pair of fluorescent lights up there, and I'm going to form an image. And you see that image is curved because of aberrations, we call them, in the lens. A single lens is not a perfect imaging element. But you can put multiple lenses together if you know how to design them right. And that's what's in here. Several lenses designed to get rid of that curvature. Now if I come down here and form the same image, you see it's sharp. You see the two fluorescent light fixtures up there. And it's a flat field. It's in focus all the way across. And it's flat. So now when you present this to a piece of film or a charge coupled device array in the focal plane of this for a digital camera is what you would have, you get a nice sharp image.
Okay.
So now this is the evolution of a single lens to a modern day precision imaging lens.
Very interesting.
A pressure transducer to measure total pressure on an airplane. And the faster the airplane flies, the higher the pressure in those tubes. It's a back pressure. So the tube has a dead end at the bottom. But there's a tap on the side, and you can tap into that tube to measure the pressure in the tube, and that's what this device is designed to do. Tap into the side of a pitot tube, and then what's in here is a welded diaphragm, and the pressure pushes on the diaphragm, and depending on the pressure, of course, the diaphragm deflects different amounts. And now we have an optical signal that we can inject in here and get a signal out, and the optical signal is proportional to the deflection of that diaphragm. And a device similar to this one, this is a prototype, was placed on an F-18 fighter jet and tested by NASA in a series of tests.
What has been what you would consider one of your largest challenges in your career?
Well, that's a good question. Probably, when you have a project, first of all, I've been fortunate to be able to win projects from various government agencies. It's not just always working for a company, but also being given the responsibility for a large project that the company is interested in, but they were successful in getting funding from a government agency. Some of those projects are difficult, and you don't always get the results you hoped in the beginning, but you always learn a lot. And so it's in those time periods in between when you start the work and when you're finished that you lose some sleep. And one of the projects was in a coal liquefaction plant in Alabama, and it was hot down there. And then you go into this plant and it's really hot. And so I spent hours on a project like that, and it was difficult to get up and work on it every morning, but it turned out well. And we were able to measure pressure at very high temperatures using this kind of technology.
Interesting. Yeah.
Now coal liquefaction is not an economical process, especially now.
Right.
But back in the early 90s, DOE was very interested in that, the Department of Energy, because we didn't have all the we didn't have all the oil reserves that we have since found.
And natural gas.
And natural gas, and we needed a way to increase our amount of oil, and liquefying coal is one way to do it. But it's a very dirty, messy operation. It's very hot. Equipment doesn't last very long because it has to withstand these high temperatures. But the pressure transducers work just fine.
Interesting.
Yeah.
A couple of your, what you would say, the most significant accomplishments, and maybe you mentioned them, but it'd be nice to say this is
No, it's my
thing
wife
I'm
and
most proud
family.
of.
I don't have any question about that.
That's wonderful. Wow. Yep.
But if you're asking technical accomplishment, yeah, I have several, and you can measure them according to the economic benefit they produced, and that's generally the 80-20 rule. Have you heard about that?
Yeah.
The 20% of my patents have made money for the companies that own them.
Okay.
When I was an employee, I had to sign over my patent rights. So the companies I worked for profited from what I did. But then, you know, there are other patents that have value, even though they're not producing an economic benefit. And I'm trying to think, you know, which of them might fit into that category that has value, but economically is sort of neutral. And I'm thinking now it might be the hydrogen sensor. And if you know, the auto companies have been looking at different ways to power automobiles. Fuel cells is one of them. And fuel cells burn hydrogen. And they have a chemical reaction going on instead of a combustion engine. So you have the chemical reaction that creates the hydrogen, and then you burn the hydrogen to get propulsion. So now if you have this kind of a thing in your garage and you've got a leak, and then you can have hydrogen build up in your garage, and if you turn on a light switch, you could explode your home and your garage. You know, these are the kinds of things that people don't think about when they're
Right.
developing technologies, but that's a possibility.
Huh.
So I invented a hydrogen sensor that would, just like a smoke detector, would set off an alarm if you
Wow.
exceed a certain limit of hydrogen.
Sounds like that's going to be very important at some
Yeah.
point here, right?
Yeah, but that's expired. So
Okay.
now it's in the public domain,
Oh, wow.
and whoever wants to use that technology is welcome to have it.
Wow.
Yeah.
An aha moment. So, you know, sometime in your career when you said, wow.
Yeah. Well, that picture is in the slideshow you're going to see tonight. And that was when I was working for the National Security Agency in 1978, and we were developing waveguides so that we could control light on a wafer, similar to controlling electronic signals on an integrated circuit. And I was in the forefront of that technology in those days, and we put waveguides on a material called lithium niobate. It's a ferroelectric material that has two indices of refraction. It's called birefringent, and if you look at writing through it, you get a double image just because it has two refractive indices.
Wow.
Yeah, and we were putting waveguides on the surface and testing them, and we made one that worked.
Wow.
And the one that worked was in that photograph. And so that was an aha moment. That technology is now used in all the wafers that support optical communications. And as I mentioned before, if you have a Verizon Fios or an AT&T UVerse and you have an optical fiber coming into your home, you've got a wafer just like that.
Speaking with John Berthold from the class of 1963, obviously we're very, very proud of Dr. Berthold for being one of our alums at Susquehannock High School, but being a local New Freedom guy who certainly has made it very, very, have had a great successful career, but probably most importantly, when I read your bio and when I think about you, all the uses that have really advanced
Yeah,
everything that we use is just amazing.
yeah. And you don't think about that when you're doing it.
Okay,
The uses fall out of it after you're done.
yeah, amazing. But there's probably not a house in southern York County that wasn't touched by some of the work you've done.
That could be.
And that's, when you
Yeah.
think about that, that's,
Right.
I'm not sure there's anyone else perhaps that could say that.
Yeah.
It's truly, truly amazing. Talked a little bit about your family, how much they mean to you. Certainly our graduates and community members at commencement will hear your words. But what advice would you give to young people today?
Yeah. Well, the ones I like the best are finish what you start. See things through. Think before you act, and evaluate yourself, the consequences of your actions before you take action. And then work hard. And don't be afraid to try new things, but try them and work hard. And do what needs to be done.
Yeah,
Yeah.
excellent advice for all of us. Final words, anything you'd like to share with our community?
I'm happy to be here. I'm honored, and I'm looking forward to speaking to the class tonight.
Okay.
the class of 2016.
Yeah. Dr. John Berthold, again, we're very, very proud of you, Dr. Berthold. Thank you for coming back from Ohio to be with us this evening, and all your contributions to all of us. And again, next time I turn on my TV, I'll think of you.
Okay.
And
Thank you, Wayne.
I appreciate that. So, for Mr. Mark Ruhl and Warrior TV, I'm Wayne McCullough. I'll see you next time.